Lesson 8D, Conservation of Momentum. The law of conservation of momentum states that the sum total of momentums, or momenta for plural, of all objects in a collision or explosion is conserved. That means no momentum is lost and no momentum is gained. The amount is a constant. Formally, it states that the vector momenta before the interaction is equal to the vector momenta after the interaction. For a two-body interaction, the total initial amount of momentum of the two objects must equal the total final amount of momentum of the same two objects. The sum total must stay the same, although the momentum for each object may have changed. The formula for momentum is mass times velocity, so if the masses of the two bodies do not change during the interaction, then their velocities must be what changes during the interaction. Simply, the sum of initial momentums equal the sum of final momentums. An example of this is seen in Newton's cradle. When a single ball with a set mass is dropped and reaches a certain velocity, it will strike the balls with an amount of momentum x. When it strikes the stationary balls, it stops. Its momentum becomes zero. Due to the law of conservation of momentum, the momentum must be somewhere. It cannot be lost. The energy is transferred across the stationary balls to the last ball in the chain, which gains all of the momentum from the first ball of similar mass, and due to its similar mass reaches the velocity of the first ball and rises to the same height as the first ball, and then it stops and drops back down. The transfer of the momentum now repeats back to the left. Here is a brief video of Newton's cradle in action. Note how the balls subsequently fall lower and lower. This is not due to the failure in the conservation of momentum, but the loss of energy due to friction, which we will talk about next unit. There are two types of interactions in grade 11. One is collisions, where objects come together, and there are explosions, or recoils, where objects move apart. In Physics 11, we will look at interactions in a single plane, so no components. But we will have objects moving in opposite directions in the planes, so it's important to keep track of our positive and negative signs denoting direction of our vectors. There are in turn two types of collisions. The first type is where a moving object collides with a stationary one, such as the sphere hitting the stationary man. The momentum of the moving object is the amount that must be conserved after the collision. The second type is where two moving objects collide, such as a rear-end collision like the car and the bus, or where both objects are moving in the same direction but the faster one catches up to the slower one. Or it may be a head-on collision like when we shoot a neutron at the nucleus of an atom, which we do in particle accelerators. In these cases, the sum total of momentum of the two objects before the collision must equal the sum total of momentum of the two after the collision. For explosion or recoil, the initial momentum is zero. That makes the final momentum zero as well. In order for this to occur, the two objects must be moving in the opposite directions, such as the air and the balloon moving in opposite directions, the air and the hovercraft moving in the opposite directions, and the two carts being pushed by a spring in opposite directions. Let's look at some general models of these types of interactions. The first is moving mass 1, which collides with stationary mass 2. Mass 1 has momentum, while mass 2 has none. When mass 1 collides with mass 2, the momentum that mass 1 had is now transferred to both objects of mass 1 and 2. As a result, the two masses move off in the same direction at a slower velocity than mass 1's initial velocity. Example number 2 has mass 1 moving faster than mass 2 in the same direction. Mass 1 has momentum as well as mass 2. When they collide, the sum of initial momentum is transferred to the two masses, and they move off together with an intermediate velocity. In example number 3, the two masses have a head-on collision, where mass 1 moves to the right and mass 2 moves to the left. Their sum of initial momentum is conserved after the collision, and they move off in the direction together depending on which mass has more initial momentum to begin with. In this case, it's to the right. Last is an explosion or recoil, where both masses initially have zero velocities, which means initial momentum is zero. When they explode outwards, they will have to move in opposite directions with the same momentum. If they are the same size, that means they will move with the same speed, but in opposite directions. If they have different masses, the larger mass will have a smaller speed than the smaller mass.